Good afternoon, everyone. My name is Jin Lin. I'm from the program system group at Uber. Today, I'm going to present automating efficiency improvement by provide guided optimization. So here's the agenda for today's presentation. So first of all, we will discuss the motivation behind using PGO at Uber. And then we will dive into the design and implementation details. And next, we will explore how to enable the PGO for Uber Go services and deploy them into the production. And after that, we will discuss how to evaluate the PGO performance impact. And finally, I will wrap up with the future plans and conclusions. Okay, so now let's start with the motivation behind using PGO at Uber. So in Uber, we have more than 26 Go microservices in Go monorepo. And reducing the resource usage is very important, especially for service running in the constrained environments. And optimizing those frequently execute code paths is very important for reducing latency. And PGO is a well-known compiler optimization that improve the CPU efficiency. So before version 1.20 in Go compiler, there was no PGO implementation. So which projects are to explore these optimizations. So implementing the PGO at Uber came with a set of challenges. So first of all, we have to make various optimization decisions and ensure the compatibility and the stability. And the build and the deployment process needed the adjustment. And for example, we need to measure the PGO compile time and how to enable the PGO in a Bazel build and the U build, and how to conduct the CI test for the PGO SDK. And we also have to carefully plan to incrementally roll out those PGO-enabled services. And finally, the accurate performance measurement was crucial to assess the PGO impact. Okay, so let's look at the timeline of those key PGO features. So PGO-driven inlining was released in the version 1.20 and providing about a 4 to 14% performance improvement. And then in version 1.21, we introduced a PGO-driven de-virtualization. And you can further optimize the execution efficiency. And we have upstream the profile preparation tool, which will be released in the version 1.23, aiming at improving the PGO compile time. And beyond these features, we are working on several upcoming features. And so these include layout optimizations for the functions and the baseball blocks to improve the execution time. And we also focus on the memory management improvement to reduce the overhead and to increase the performance. And finally, we have the machine-specific optimization, such as just network allocation based on the profile, which will better utilize the hardware capability. And the PGO framework at Uber is a continuous optimization process. So the profiles are collected during the Go PGO compilation process. And the optimized executable file will be deployed into the production. And we have the preparation tool to improve the build time. So now let's move to the design and implementation of the PGO. And so here's the Go PGO compiler framework. So it starts with a robust profiling infrastructure. So the profiling is collected and used by the different compiler phases to guide those optimizations. So for example, so the provider can tell you which call size is hard, is frequently executed, or which call size is infrequently executed. And this frequency will be denoted as the hardness of the call size. And so the basic idea for the inlining, for the PTO-driven inlining, is to enable the inlining for those hard call size and try to disable the inlining for the cold call size. And the advantage is which it can improve the memory locality to reduce the number of instructions and CPU cycles. And more importantly, it can also help the escape analysis to determine more variables to be assigned into the stack space. And so it can also save the memory allocation. So before we jump into the PTO-driven de-virtualization, let's define what is a de-virtualization. So suppose you have a call to an interface, and the interface will have multiple implementations. So the compiler usually generate an indirect call, and so you will look up the correct method at runtime based on the type information. And then in certain cases, the compiler know, oh, there's only one type, so you just replace this indirect call with a direct call. And this transformation is denoted as a de-virtualization. And PTO-driven de-virtualization extends this concept to the situation where the compiler cannot determine the type. So let's assume that the provider will tell you this interface call calls some target most of the time. And then the compiler will generate a runtime type check. So if the type check is successful, it will cause a direct call. Otherwise, it's just back to the default indirect call. And so the advantage of this transformation is to enable more inlining and also help the escape analysis. And we also use a profile to guide the basic block reordering. So the basic idea is to place the frequently executed code together to enhance the cache locality. And we also have the function reordering at the linker step. So this is a cross package function reordering, try to improve the memory locality. And pre-process step is also very important because it helps improve the build time, make the entire framework to be more efficient. So here I want to show you how to evaluate the PTO-driven inlining for the tally benchmark. So the inliner first to decide the hardness of the call size from the profile, and then you can inline the call size by increasing the inliner budget to a larger value, or it disable the inliner for the cold call size. So in the example on the right-hand side, you can see the call to cache report is called inside loop, and then the profiling will show that this call size is very frequently executed. So, but the default inliner cannot inline this function because the body size is larger than the default threshold. And then after we increase the inline budget, then the function can be inline. So for tally, actually is a metric collection library, which is used universally at Uber. And so the x-axis is represent the name of the micro benchmark in tally. And after we apply the PTO inlining, then it can deliver average 10% improvement. And some of benchmark actually is up to more than 50% improvement. So we also evaluate the PTO inlining using the GopherCon benchmark. And the left-hand side is a micro benchmark in the GopherCon. And the PTO inlining deliver more than average 10% improvement for the GopherCon for the entire benchmark. And a lot of micro benchmark actually shows more than 20% improvement. So we also evaluate the PGO inlining for the impact for the including JSON library. So the left-hand side is shows the hardcore size in the profiling, and the default inline cannot inline those three functions because the body size is larger than the inline budget. So after we increase the inline budget, then those three functions can be inline. So it's marked in the red box. And we also notice that the PGO inliner can slightly increase the number of inlining call size. So there are about 2% increase. Okay, so now let's move to how we enable the PGO at Uber. So enabling the PGO in our build and deployment process involves several key steps. First, we collect the information. We collect the performance profile daily, and then ensure that we have up-to-date data to guide the compiler operations. And next, we will maintain a file to enroll the specific service for the GoPGO. So we ensure that only the selected service will undergo those PGO observations. And then we will perform the CI test for the PGO SDK to validate those changes and ensure it will not introduce any new stability issue. And once the test passes, then we deploy the PGO build by service into the production. And finally, we will monitor the performance dashboard to check the PGO impact. So by following all those steps, we can systematically integrate the PGO into our build and deployment pipeline to enhance the performance and efficiency of our services. So here's our providing collection infrastructure. So it is designed to work seamlessly within a distributed system in the production. So we collected the continuous profiling data from the multiple instances and merged this profile to create a representative profile. So initially, we encountered the compile time issue after the PGO is enabled, and the build time of server services is increased significantly. So, and then it's not accepted by the service owner because it affects the release build. And so we study we have a breakdown compile time data for these reading profiles into the compiler. And we found that the PGO profile passing consumes the majority of time. And this profiling reading actually occurs for every compile package. So it's very obvious we need to develop a pre-processing tool to reduce this passing. So the solution is we develop a pre-processing tool to improve the build time. So the tool reads and passes the p-profile and generate a call graph file contain all the call site information, such as caller, calling number, and weight. And this graph will be used by every package at compile time. And here I need to please note that since Go 1.23, the Go build tool will implicitly incorporate this profile pre-processing tool. So the user does not need to use this tool implicitly. And the build time overhead actually with this PGO has been reduced after we employ this pre-processing tool. And so previously we can see more than 100%. And now with this tool, it is compatible to the default compile time. So we find the issues and also we have the CL So besides the pre-processing profile, we also use a common profile to reduce the PDO compilation time. Because Uber, we use Go repo and the Bazel build, so the build result will be cached if the profile has not changed. So by this way, we can reduce the CI testing time. And for a service which does not have profile, we also use a common profile to try to improve some performance. So now here's how we enable the PDO and tune the threshold. So first we load the service into the file PDO compilation YAML file, and then we tune the threshold for the PDO optimizations. So the first is a PDO inline budget. So for example, if the body size is larger than this value, PDO inline budget, then it cannot be inline. And we also sort the core size by the hardness. So the second value means that if the core size is not hard enough, then it also cannot be inline. So we provide a file for the user to override this threshold. And in the bottom part of this slide, you can see that on the left-hand side, you can see the profile before PDO and after PDO. And we can see that the PDO inline 3 more hard functions. We also provide inlining tools to allow the user to specify which function to be inline, which core size to be inline, and which core size should not be inline. So for example, if we can disable the inlining for some of the core size, and then if we suspect this inlining can cause the performance regression. And I believe this tool will be very useful to identify the performance regression. So now let's move to the performance impact. So at Uber, we use P99 every 7 days to evaluate the CPU efficiency. So here's how we calculate the P99 average. So given a service, we sum up all the CPU usage across all the instances for each minute. And then we divide this CPU usage by the total number of cores allocated during that minute. And at the end, we take the P99 of the minute values of the utilization for 7 days. And we also have the CPU-based auto-scaling. So the basic idea is that we allocate more CPU resource when the CPU utilization is larger than some threshold, or free the resource when the CPU utilization is smaller than the threshold. There are challenges in the PDO performance measurement. So at Uber, we don't have A/B test performance measurement support. So it means that we cannot deploy one PDO binary onto two the same hardware with an equal RPS. And we know that the CPU usage can be affected by the traffic, by the RPS. For example, the RPS increase, then the CPU usage might increase. If RPS decrease, the CPU usage also drop. And then we have auto-scale enabled by default. And so it means that if the auto-scale allocate more CPU resource, then the CPU utilization also drop. And also, during our performance measurement period, the source code of the service might also change. So here we provide 2 different approaches to measure the PDO performance impact. One is the parametric comparison for 7 days before PTO and another 7 days after PTO. And we also have provided A/B testing across the different zones. So here we pick the top 6 services to measure the CPU allocations when the PTO is on and off. And the y-axis is the number of the CPU cores. And the blue lines represent the number of CPU cores when the PTO is enabled. And the yellow line represents the number of CPU cores when the PTO is disabled. And so we can see the number of CPU cores is reduced since April 18 when the PTO is enabled. So it's very obvious. But because of the autoscaler and RPS, then we need to find a way to prove the reduction of these CPU cores is related to the PTO combined observations. So let's move to how to select the performance metric. So basically the performance measurement period is 7 days before PTO and 7 days after PTO. And we cannot use CPU utilization or CPU allocation to measure the performance. So I can show you the example on the left-hand side. So you can see that in June 6, we have the CPU utilization drops because on the same time the autoscale kick in and allocate more CPUs. That's why it dropped. So it's not related to any PTO effect. And also on the right-hand side, you can see that in July, the CPU usage also dropped compared to the June 30th. The reason is that the RPS dropped at the same time. Then the CPU allocation is also not reliable. One example here is if the RPS drop and make the CPU value drops, and now if the autoscale kick in, then it will free up more CPU resource. And so this CPU allocation reduction is not related to any CPU efficiency. So based on this fact, we use the RPS per CPU core usage as a performance metric. So now we pick top 6 Uber services for the performance comparison. And these 6 services actually consume more than 10,000 CPU cores. And then we compare the RPS per core before PTO and after PTO for 7 days. Based on the RPS core ratio improvement, then we can project the cost saving with the PTO. And in addition, we can also compare the absolute core number before and after PTO. And then for this top 6 service, we can see that the projected cost saving is comparable to the real cost saving. And we can see some of the service actually improvement is about 5 to 6%, and some of it is more than 10%. And so we have a second approach to measure the PTO performance impact, which is A/B testing across the zones. So given the same source code of a service, we build a non-PTO binary and a PTO binary. and then we deploy the line PDO binary onto the control group. And then we deploy the PDO binary on the treatment group. And now we can use the RPS per core as a performance metric. We denote this one as a CPU efficiency. And so it represents the request per second that one CPU core user can handle. So that means this value is the larger, the better. And so now we have the relative CPU efficiency, which is the ratio of CPU efficiency of the treatment group to the control group. So that's how we evaluate the impact of PTO. So here I can use one example and to show how we measure the performance impact for the service doubling. So from the March 24 to April 22, we deploy the line PTO binary on both control zone and the treatment zone. We know that the hardware are different between the control zone and treatment zone. The RPS are also different. So it's not apple to apple comparison. But so what we want to hear, we compare the CPU efficiency between these two zones. And then you can see that the difference is very similar. So for the first 5 weeks, the difference is between 9 and 10. And for the last week, we deploy the PTO binary onto the treatment zone. And you can see that the difference is reducing from 10 to 5. The reason is the hardware on the treatment zone is slower. And then the PTO optimized binary can make it more efficient. So that's why the gap is smaller. So here are the service we measure using the A/B testing. So the y-axis represents the number of service, and the x-axis represents the improvement percentage. And you can see that the average, most of the service is about from 1% to 8%, which is about 4%. So here I want to demonstrate the effectiveness of the PTO using a micro benchmark. So in this demo, we will observe performance metrics from the benchmark output, such as the number of nanoseconds spent on each operation. And the first step we want to do here is that we collect the CPU profile, which will be used to guide the inlining process. So this step is how we collect the CPU profile. And then we will use a pre-processing tool to pre-process this profile to generate a core graph file. And next, we will recompile this benchmark and run this benchmark without creating the profile, because this version will be served as our base version for the performance comparison. And we avoid using the first version because the profile collection might slow down the performance. And in a final step, so this is how we and this is base version. And then now we feedback the profile into the compiler, and this is the optimal version. And so we will use a bench state to compare the performance between the base version and the optimal version. And as you can see that this number, So using the base state, we can see that the PDO inlining can deliver about 8% improvement. So now let's move to future plans and conclusions. So looking ahead, we will deploy additional PDO-driven compiler optimizations. First, we have the function and baseball reordering, which can help further improve the execution efficiency and by enhancing the locality. And we are working on the memory optimizations to focus on the slice and go within stack to reduce the memory overhead and improve the performance. And finally, we have the machine-specific optimization, such as allocation, to better utilize the hardware. And these upcoming features will unlock even greater performance headroom and further optimize our Go microservices. So here's a preview of the baseball reordering. And so the example is actually from the encoding JSON library. So in this example, the perf file shows that there's a very hard loop at 960. And the compiler actually, so the rest of code actually are never executed. So the compiler can place the hard code together to improve the locality. So here we present the output of the baseball reordering. So on the left-hand side is a default output without the profiling, and you can see that the basic block 1, from the basic block 1 to basic block 7, it represents the code for the loop entry, and the basic block 114 to 120 represent the code after the loop. And those code actually, so without profile, the basic block, so you can see that the pound number, pound 0, which represent the lexical order of those basic blocks. And without profile, the block 7 and the block 114 are placed much far away. And when you're using profile, you can see that block 7 and block 114 are very close. Because it can demonstrate the baseball reordering with profile can improve the memory locality. So here is an experimental result. We are using the two benchmarks to evaluate the performance impact from the PDO-driven baseball reordering. And for the GoJSON benchmark, the base version we are using is a PDO inlining. And the option version is a PDO inlining plus the baseball reordering. Then the average improvement is about 1.5%. And for some of the micro benchmark, it's about the improvement can be up to 6 or 7%. And we are also using the Google Street benchmark to measure the performance. And we found that the PDO-driven baseball reordering can improve the Go build time by 5%. Okay, so now we're also working on improving the memory allocation based on the memory profile. And so here's one example. At 141, when the slice is allocated is smaller than the size needed at runtime, Then the subsequent append operation will introduce the new memory allocations and the data copies. And so the solution is we want to feedback the memory profile to the compiler and teach the compiler to allocate correct size so you can improve the efficiency. Okay, so now the conclusion. So we see that the PGO inlining has been proved to be effective. So it can provide about 4% performance improvement across Uber's free-ride service. And we also discuss different approaches to measure the performance, PGO performance impact to make sure we can accurately capture the benefit. And looking ahead, we are exploring the additional compiler optimizations, such as Bazel reordering, to unlock more performance gains. So enable the PGO at Uber actually requires a huge team effort. So I want to thank to all my coworkers at Uber and the Google Compiler team for their big contributions. Thank you for attending my presentation. I'm happy to answer any questions offline.